Hello again. So today we're going to carry on with this theme of numerical instability, this very important concept. Last time I showed you it in the context of a decaying solution, and one example where numerical stability was occurring where it followed the decaying solution, and one where it was unstable where it didn't. Today we're going to use what I call a recursive example, how you take from previous steps to the next step to show examples of how random error can grow from the initial conditions and cause problems with stability. Okay, so let's look at this recursive example of numerical instability. So for this one, I'm just going to use the board on its own, remove my image down on the top left-hand corner so we can use the whole board unimpeded in that sense. Okay, so this is the whole aim of this example is to show. So the aim here is to show show how the round-off error epsilon can grow unbounded for an unstable numerical method. So we're going to pick a method that turns out it's unstable when you solve it numerically. And this is an example that's been in this module for many years. It's reasonably artificial, but it's got a lot of it's a very interesting start at understanding this issue of the random error. So we're going to consider the recursion relation 3 times xn equals 10 xn minus 1 minus 3xn. So it's analogous to a time stepping method that we started looking at last time, where one step and depends on two previous values. n minus 1, n minus 2. But we call it a recursion relation because it's not strictly speaking a time stepping method, right? But if you like this, try and find a link between this and things we'll do later on. That's where the link comes in. So the point is that the new value at any point at n is dependent on 10 times the x n minus 1, 3 times x n minus 2. So it's a recursion. And what we're going to do is actually just try and determine what the true solution is for this system before just applying it numerically. So before we go there, we must also state the initial conditions. So we have we have initial conditions x at n is 0 is 1, x at 1 is a third. So this is a slightly different type of relationship in that we need two initial conditions. Okay, so this sometimes catches people out. The reason we need two initial conditions is that the new value xn is dependent on two previous values. So we have to start off the system with two starting values. So we start it off with x is 0 is 1 and x1 is a third. And that'll turn out to be important about how we set this up. Okay, so we start off with 1 and then we set the next one is a third and then we set it going, if you like. Okay, so with those initial conditions, the two initial conditions, the true solution is then xn is 3 to the power minus n. Okay, so I haven't derived this analytically. What I'm going to do is just check that this is so by substitution. Okay. So we check this by substitution into the recursion relationship. So if we substitute into the right hand side, remember was 10xn minus 1 minus 3xn minus 2. So the right hand side equals 10 times xn minus 1. So we just put substitute n minus 1 in there. Remember the minus sign. So that's 10 times, I'm just going to do a dot there for times, and then 3 minus n minus 1, so that becomes plus 1, yeah, because of the negative sign. And then minus 3xn minus 2, 3 to the power minus n plus 2, okay. Okay, so we can factorize this quite nicely because we have a common factor of 3 to the minus n emerging here. Let me just circle it. There's a 3 to the minus n in there. There's a 3 to the minus n in there. So we can take 3 to the minus n out. And that gives us, and we must remember this extra 3 from this power of 1 there. That gives us 10 times 3 to the power of 1, which is 30. Minus 3 times 3 to the power of 2. 3 times 9 minus 27, which equals 3 times 3 to the power n, which equals, now 3 to the power minus n of course is our initial, is our trial solution x to the n, so that's just 3 times x to the n, which equals the left hand side. So this solution works for these initial conditions. The other thing to note that it also works for the initial conditions we've set up. So we've had x0 is 1 and we've had x1 is a third. Okay, so that shows, I mean, essentially this solution says that each step you're dividing through by 3. Well, if x0 starts with 1, then the next one will be a third. So this means that with these initial conditions, we're purely projecting onto this initial condition if there's no error involved. So that's one solution. There turns out to be another solution as well. Let's just find that. So 3 to the minus n is one solution. That's the decaying solution. So this is where the analogy with our exponential decay in the last video comes in. So we've got an exponential decay, we've got an exponentially decaying true solution here, except that it's not e to the something, it's 3 to the power minus n. So, and we know that it works for this recursion relationship. There's a second solution xn equals 3 to the n. Obviously that's not stimulated by the initial conditions per se, but we will see it comes into play. And this is not such a helpful solution because it's exponentially growing. So exponentially growing. Okay. Let's just check again that this fixed. So we do the right hand side, which equals 10 times x to the n minus 1, 3n minus 1, minus 3 to the xn okay, and this time we've got the common factor of common factor of 3 to the n coming out. So we factorise out that common factor, and then we're ended up, but this time it's 10 times 3 to the minus 1, so it's 10 over 3 minus 3 times 3 over 2, so 3 over 9. Okay, and if you work that through, that's obviously a third. 10 third, that leaves you with 3 times 3 to the n, which again is 3 times x to the n, our initial value, which equals left hand side. Okay, so it proceeds quite nicely. So we've got these two possible solutions to the equations. We have a decaying one and a growing one, and that's why we picked this, what initially seemed maybe quite a random recursion relation. Well, it's not random, it's because it has these two solutions. It has a growing one and a decaying one. And so the sort of general solution now is a superposition, and you can just add them, of the growing and decaying solution. And we have these constants, A and B. We'll just have where A and B are determined by the initial conditions. So when x0 equals 1 and x1 equals a third, those are initial conditions, then that means that implies that A equals 1 and B is 0. Right, because you've set your initial conditions up cunningly that they just project on the 3 to the minus n mode, but not the 3 to the plus n mode, not the growing bit. And that's very important. So we've got a true solution that should decay. Right, so this is very analogous to the more qualitative picture I was giving you last time with exponentially decaying. But the key is when you do a numeric, so this is the analytical solution. Its analytical solution is x at n equals 3 to the minus n. It's decaying. What's happened there? Sorry. But the key thing is this is the true solution. But what if you were to add a little bit of error onto these numbers? If you were to add a little bit of error, a round off error, suddenly you might bring in this growing mode into play. And that's where the numerical stability arises, you see. So we're saying the true solution is decaying, but because of round off error, when you do a computational simulation, you know, we may get the growing solution. So let's so consider including a round off error in the initial conditions. So we redo it now, but with a round off error. And this round off error will always be present in any computational simulation you do. Remember, it was 10 to the minus 16 on my computer. You can just type EPS in MATLAB. It gives you. So we have x0 is 1 plus epsilon. So what we're doing is, in this first one, is introducing the round off error but then we have to set up x1. Now in this case, what I want to do is make a clean example. So what I'm going to do is make it that the round off error projects completely on the growing mode. I don't have to do it that way, but it just makes for a cleaner, simpler example. Remember that we're using this not for the sake of doing the mathematics primarily. Primarily we're doing it to understand how round off error contributes to numerical instability. So what we're going to do is make the second contribution in the second one 3 epsilon. The reason being is that this is 3 lots of epsilon. So with this choice, this is a choice I made, within this will project onto 3 to the n solution. Okay, so this is, people don't like this often, but it's a choice I've made to make a nice clean example, and it's what we've done in the past. Okay, so that hopefully that makes it clear. So when we do that, so when we repeat that and evaluate our constants, it means that actually then A, our constant, is still 1, but now B, before it was 0, is epsilon. So our solution now has a decaying bit, but it has this unhelpful bit. So this is called, sometimes called parasitic solution or instability. And this is why we set up this, what initially looks like a fairly artificial example, but it's a very nice example because we know the true solution is this first term, 3 to the minus n, but now we've put in some random error, very small error, but because it's multiplied by this exponential term, and that's the point, a very small error gets multiplied by exponential growth, it dominates the solution later, and it's parasitic, it's nasty, it's numerical instability. Okay, so that's the kind of background math, and so hold this solution in your minds. So I'm just going to put a box around it. Okay, so you have your true solution. So that's your true solution, if you like, and that's or instability. Okay. So in the next video, I'm going to then show you how this recursion relationship behaves when we compute it. Okay, so if we go back to our original one without the parasitic solution, just the true solution, just do it on paper, we get the true solution. Okay, but now if we repeat with this this recursion relationship, right, with our computer, that will always have the random error in the initial conditions. And what I want to show you is that random error will corrupt the solution in the way demonstrated here. Okay, so this is actually incredibly powerful example. It's a little bit more mathematical, a lot more mathematical than the qualitative picture I'm giving you. But what I'm trying to give you is different angles onto this sort of this challenging concept of numerical stability. I'll do the MATLAB example next, and then we'll move on to sort of some more standard time-stepping methods and do the instability, repeating a little bit of what you did last year, and then extending things a lot further. So hopefully, after once we do that, you're getting a nice broad picture of what numerical instability is about. Okay, so see you in the next video. Okay, bye for now.